Hello everybody, this is Martin of VEX Forever and welcome to the second episode of Let's Make a PID Loop. So last episode we just set up something very simple. Let's delete that for this example. Last episode I just explained the base setup of our project and some basic stuff like how do we easily control the base movement forward and back with a very simple user function, and finally we set up the base control. So let's the base control parameter. Function with parameter. So alright, let's dive right in. Today I want to cover three things. First is how to convert between the inches the robot moves to the actual counts the robot moves. Hopefully we're gonna do that neatly in another I'm thinking about user function, actually function with parameter, and we are going to do a simple timing feature for our PID loop, and also we're going to set up our PID loop and constants, and hopefully we'll hit the proportion today. Alright, so let's start. So first, in the PID base control, I will just set up a while loop because we always need a loop to constantly update values. So in this case, I need a while loop. So in this case, right now, I'm just going to put true, and it's just a loop. And for the wait time, I will use 40 milliseconds actually, just to get some decent resolution for the derivative, and which I will explain later in the derivative video. So let's go. Wait 1 millisecond, 40. Let's do that. Sounds about right. So in the PID base control, we need our target. So let's put a target right here. It's integer target. However, we all know that the way encoders work is that as you spin the wheel, the encoder counts the ticks. How many ticks is counted, and it gives you back a very large value. Usually, the value has a lot higher resolution than what we usually think of, usually in inches or feet. However, what we want to do is that we don't want to directly deal with these values. Although you can, every time you can convert things manually and say that, alright, I want the robot to move forward 627.2 ticks, which in this case, in our error, I've already calculated, it will be 6 inches. We can do that. However, what we want to do is that I want to tell the robot move forward 1 inch, and the robot moves forward exactly 1 inch. That's what we want to do. So we need a function, a user function with parameter that directly converts our inches to the ticks with a higher resolution that the robot can read. So how we do this? So first, let's get something straight. Our error or our reading is in ticks per second. Just ticks. It's in ticks. And as I have already researched for the integrated motor encoders, is 600 in high torque mode. In high torque mode, it is 627.2 ticks per revolution. We want to convert the ticks. We want to input a inch value, and then we want to actually convert this inch to the tick value that the robot can actually read. So how would we do that? And in this case, what we know is that for every one turn of the wheels, and the wheels, we assume that they are 4-inch wheels, 4-inch diameter wheels, just basically omni wheels. We know that that is equal to 627.2 ticks. And in this case, because we have two encoders, one on each side, the main error we want to use is actually the errors that's multiplied by both. The errors of two sides added together. So basically, we need to multiply that by 2. So one turn of the wheel how long? How many grounds does it cover? So the one turn 1 turn of each wheel. I mean, how long does it cover? And to do that, we need to calculate the circumference of the wheel, which is essentially the circumference of a circle with diameter with 4, which is 4 times pi. 4 times pi inches. So basically, we know that from this logic, we know that for every 4 times pi inches, that is essentially the same thing as what the computer reads as 627.2 multiplied by 2 ticks. Excuse me. I apologize for that. Alright, so we just talked about that 4 times pi inches is equal on the base. In our case, is equal to 627.2 times 2 ticks. And now we need to calculate a constant that can convert inches to ticks, which is essentially how many ticks per inches. And how would you do that? So what we want is ticks per inches. Ticks per inches. The ticks per inch is equal to, so what does it equal to? So basically you divided both sides by ticks, and on this side we divide both sides with 4 times pi, 4 times pi, so it's essentially 627 multiplied by 627.2 multiplied by 2 divided by 4 times pi. 4 times pi. And I am going to grab my handy dandy TI-89 calculator and calculate that value for you. And I have already calculated for that value before, but just to make sure, let's run through that again. 627.2 times 2 over 4 times pi. Have a pi button, which is convenient. Is equal. That equals to. I'm just gonna make it precise. 99.82198. So essentially, what this is saying is that what we just calculated is that for every 1 inch, your robot moves with a omni wheel, with IME, with the error equal, or excuse me, the values or the measurement being the 2 IMEs added on both sides, with 4-inch wheels with high torque gearing. For every inch this space moves, the reading of the encoder is 99.82198, which is basically the same thing as 100, but in terms of the in terms of absolute accuracy, we are going to keep the value as this. So then let's make a user function with parameter so that we can easily convert the inches to the ticks, so that the computer can read and process at a much more precise level. Because if we convert the ticks to inches, that will be a much lower resolution, and we always want to keep the resolution high. That's why we use 2 encoders. And so let's do this. Let's do integers. This is inch, 2 ticks, and our parameter is actually float, because we want to type float the inches in decimal places. For instance, we say 0.5 or 0.6 inches, or 6 to 12.5. So let's go float inch, and don't forget about your brackets. You got your inches, and then we want to define a variable integer, which is our output ticks. And then we're going to do our algorithm. The algorithm is that ticks equals to, which essentially ticks over inches multiply inches, and the inches cancel out, so we get ticks. So essentially, we are multiplying this inch variable, copy inch variable, multiply our conversion constant and factor, which is right here. Alrighty. So if you say it's 1 inch, this user function automatically outputs 99.82198 ticks, and in this case, because it's an integer, it rounds it up, so it's 100 ticks. And then finally, don't forget to type return ticks. And there we go. We have just set up our useful handy dandy little conversion function. So right now we just defined an integer target, and let's continue to work. Let's go ahead and set up all the things we need. And right now we are really working on proportion, so let's go ahead and set up the proportion part. Let me see how much time I have left. Alright, so I just saw that I just did like a 10-minute video, and I really want to keep every episode short and sweet, so that I guess I will put proportion in the next video. And yeah, it's kind of sad, but I really do want to make things like a little bit slower so that you can just fully get the idea of what I'm actually doing. And even if you don't get some of the stuff I'm doing right now, or this is not a very comfortable way in which you usually program in Robot C, it doesn't hurt to learn it, and it's actually really useful. And as the program develops, you can see everything connecting up really nice and sweet. And I'm gonna call this episode right now. Next episode we're gonna talk about really getting into proportions and do the cool stuff, the main part of what makes a PID loop work. And this is Martin of VEX Forever, and I will see you in the next video.